Okay. I'm not sure why it's not saying anything. Okay. All right. So a lithotripter uses shock waves to break apart kidney stones that also inside the body. Okay. Didn't know that. Shock waves, I hear that's terrible if you get those. I hear it's awful pain. Shock waves generate one focus of an ellipsoid, a three-dimensional shape with an elliptical cross-section. Reflect to the stone position at the second focus. Okay. Write an equation for the cross-section of the ellipsoid with the dimensions shown. How far apart are the foci? Okay. That's pretty simple. What's the major axis? What's the length of your major axis here? What's the length of the major axis? 28, yeah. What's the length of the minor axis? So what I'm going to do, hey Ethan, is I'm just going to put the center at the origin, kind of make it easy for myself. And it's pretty simple. X squared over 14 squared. Does that make sense? Right? Because wouldn't this be 14? That blends a little too much with the colors. Wouldn't they be 14? And wouldn't that be 8, right? Because you're going 16 this way, so half of that's 8. 28 that way, half of that's 14. So that's pretty simple. And how far apart are the foci? So they want 2c. Remember, c is the distance from either center, from the center to either foci. The form is c squared equals a squared minus b squared. So what's c squared equal, guys? 14 squared, which should be 196 minus 64, which is what, 132? Yeah, which is some wacky. Does that have any factors that are perfect square? 4, yeah. So that a little too early. 2 root 33. Am I correct in assuming that? So then how far apart are the foci? 4 root 33 exactly. Which is, because root 132 is between 11 and 12, so 11 point something. So not a terribly exciting problem. I got better problems than that, but I think the takeaway here, let me drop the lights to you guys. I think the key takeaway is a model, right? When you model, we try to come up with like models for that. Oh, so much better. Try to put this center at the origin, make it easy for yourself, So when you try to do this, so then you can easily identify all the parameters of the ellipse. I think that's what I would suggest. So hopefully you guys felt pretty good about that. If we have time, I'm going to show you another kind of crazy word problem. They get to be pretty fun because they're kind of like a puzzle to solve. But we're good on that one. Does that make sense?
Not always how it's like some things. Like
Yeah, we model put the center at the origin. Yeah.
Like if something's bouncing from one focus, like off the walls, it's always going to go to another.
It should. I think that's way. Yeah. I mean, the physics of it, I suppose. I don't know. Actually, since you brought this up, this is hold on. Where's this word problem? Really good one. Yeah, that's my favorite ones. Actually, I made this one, so I'm pretty proud of this one. Okay, so hey, we're in an election year, right? So it's kind of cool. But like, this is actually true. This is totally true. So where the president sits, it's the Oval Office, right? And the president's desk is at the focus. And if you have it sound engineered properly, apparently the president can actually hear all the conversations in the room if the president's sitting at the focus. I guess. I don't know. But anyway, assuming that the major axis is 36, the minor axis is 28. These are the true dimensions. I looked it up. And the president's desk sits at one of the foci. And the fireplace is at one of the vertices. That's the endpoint, right, of the major axis. What is the distance in feet between the president's desk and the fireplace? Well, I mean, that's not terribly hard. I mean, you can figure out A and B and then do the formula, but just kind of a neat problem. So Anyway, maybe I'll have you guys practice it when we start doing review. I'll put this in the review guide. There's some other good problems too. But anyhow, let's keep moving. Let's take a look at page 12. So I'll do 8 with you guys, and then have you guys try 9 and 10. So let's take a look at 8. So you have to write an equation of an ellipse in standard form. The vertices are 0, 4, and 4, 4. So 0, 4, 4, 4. And where's the center going to be?
2.
Yeah, good. Now, that's going to be the major axis, right? Because they say that the minor axis is length of 2, so that's the minor axis is going to look more like this. Does that make sense? What's your A value and what's your B value? You guys should know this. A is what? And B is 1. Okay. So C squared has to be A squared minus B squared, which is 4 minus 1, which is 3. So C is root 3. I just cannot do 3. It's black me here. There we go. Okay, C is root 3, right? Okay. Let me fix that because that looks a little messy. Cool. So write the equation. Well, that's not hard. That's just x minus 2 squared over 4 plus y minus 4 squared over 1 equals 1. Okay. And the coordinates of the foci, how would you write that? Yeah, they're both going to share 4 as a y coordinate. So go Sebastian, what are you saying?
2 plus minus 3, 4.
Yeah, because it's going to change x, right? So 2 plus or minus root 3, comma 4. Exactly. Because they both share the same y coordinate, but the x coordinates change. One is root 3 more than 2, one is root 3 less than 2. Does that make sense? And root 3 is like 1.7 something. So I didn't draw it so accurately, but it's good enough. Like maybe 0.28 and 3.7, whatever. I don't know. So okay, so hopefully that seems fine. Just reinforce what we've done last week. So for 9, remember what you have to do. You have to complete the square. And for 10, you have to write an equation with those parameters. Let me zoom out a tad. All right. So I'm going to freeze my screen and work on them. Let you guys work on. I'll walk around, make sure you guys are doing okay. And then we'll move on to hyperbolas after that. And we'll pull the 4 out first, guys, when you group the x's. Be mindful of the scale for the x-axis. It's a little wonky. I guess every tick marks half units. Likewise for the y-axis, but just don't. The label y-axis is more clear than the x, I guess, or more detailed. All right.
Oh, no.
Need some lights down. Are you guys ready? Well, that was okay. So yeah, so if you look at part A of number 9, pull the 4 out, right? So you have x squared minus 2x. Doesn't pull out from the y parts. We square take half the linear coefficient, which is -2 squared, it's 1. But you're really adding a 4, and then the other one is 4 as well. So you have 16 on the right side, and then divided by 16. The major axis is going to be vertical, clearly. Going 4 up, 4 down from the center, 2 left, 2 right from the center for the minor axis. Center's at 1, -2, co-vertices, or sorry, vertices are at 1, 2, 1, -6. Co-vertices 3, -2, -1, -2. For 10, obviously you can't do an accurate graph because the scales don't quite fit that. That's all good. Center's at 0, 4. Oh, yikes. Sorry about that. Should be y minus 4 squared. My apologies. Just realized that. Almost perfect. My apologies. Should be y minus 4 squared. Over 64, right? Because you're from my major axis is 16a and 2a, 16a is 8. Square that 64. And then c is 4. If you use the form c squared equals a squared minus b squared, you should get b squared is 48. So all's good. Any questions? No? Cool. All right. All right. Okay, let's move on to hyperbolus. All right, so let's go and clear. All right. So what is the deal with a hyperbola? All right. Let me talk about the derivation again for that. I'm not going to go into great detail. And again, I still need to share this with you guys in school, G. So it's just as lengthy as the ellipse one. But let me explain what a hyperbola is first. And then I'll kind of just gloss over the rest of the derivation because it's very similar to the ellipse part. So instead of being the sum of all points in which the sum of the distances is a constant, is the difference of the distances. So hyperbola kind of looks like this. It's like these two parabolas are going against each other or going opposite directions, something like that. So if you pick a point on that curve, and you have your two foci, if you measure the distance from that point to one foci and that point to another foci, whatever those two subtract, so that positive difference, I suppose, if I feel like that, that will be a constant. So d1 minus d2 will be a constant instead of d1 plus d2. So we have all this stuff here, right? Like, okay, cool. And b1, call it x comma y, and negative c comma 0 and c comma 0. And by the way, from the center, which is right in between these two curves, that's center. The distance from here to either vertex is called a comma 0, negative a comma 0. So that distance is a. Just so you know. That's a. And what's really happening, this is not obvious. There's actually an invisible box in the middle. And the diagonals of the box are asymptotes. And the graph has to stay contained within those asymptotes. The width of the box is 2a. The height of the box is 2b. So it's kind of like an ellipse in a way where that is a and that is b. We're going to reinforce all this in the notes. Don't worry. Right now, you guys just watching. Just so you know, that's a and that's b. Just so you know. So you have these two distances. You subtract them has to be a constant. Just like derivation for ellipse, we need another equation. We'll use a comma 0. Obviously right there. So if I find a distance, if I try to like say, okay, well, what is this distance? And what is that distance? I should do some different colors, obviously. So we have this, and we have this. Well, it's pretty obvious that the one will be I think 2a plus c. No, sorry, a plus c. Yeah. So my apologies. So this right here is I should mention this. This right here is c you got, by the way, guys, and that's c. So that distance is a plus c. And the other one's just a minus c. Sorry, c minus a, because c is bigger than a. So that's one thing that's weird. C is bigger than a in this case. So still you still get 2a. That's gonna be the constant, still gonna be 2a. Just like for the ellipse. And you kind of go through all this math, square both sides, isolate the radicals, do all this stuff. You wind up stumbling upon something like this over here. And now in this case, this is yet another formula. C squared equals a squared plus b squared. Instead of a squared minus b squared, it's a squared plus b squared. And why that is, I'm not gonna get into that. So we'll just assume it for now. If you substitute and go through all the math, you wind up getting this. Yeah, so I know I didn't gloss over it. But just know it's very similar to an ellipse, except a plus is a minus. And very important, whichever fraction is positive is how the hyperbola opens. So if x squared is positive, it's going to open left and right. If y squared is positive, it's going to open up and down, just so you know. And a squared is going to be the distance from the center. Sorry, a is going to be the distance from the center to either vertex. A could be less than b, though. That's a possibility. A squared is reserved for the positive fraction, just so you know. It's always reserved for the positive fraction. And how it opens, whether it opens horizontally or vertically, that's actually called a transverse axis, not a major axis, but called a transverse axis. So I may need to share, just for your reference, because the more I think about this, there's a lot of stuff I'm sharing with you guys. Even though I'm not going to provide this for me because that's a little too much, but this might help you guys to make sense of this. Was that from outside? Okay, all right, okay. Anyway, H and K, we can move this left and right. That's what can happen. Foci is C, the distance from the center. Either focus is C. Vertices, you have that. We don't have co-vertices so much because it's not a point on. I mean, if you want to call that a co-vertex, go for it. I don't care. But it's not a point on the curve. Now, the transverse axis is this, where how it opens. Where it does not open, I guess it's called the conjugate axis. If you want to call it, that's fine. The big one is going to be the asymptotes. How to find the equation of the asymptotes. Don't overcomplicate it. Use point slope form. You guys recognize point slope form? I know it looks really complicated right now, but if you think about it, how do you find the equation of line? You need slope, right? Wouldn't you just rise and run? Right? Just you rise up and run. Don't even worry about the whole A and B thing. That's just kind of crazy. And you know when it passes through, does it pass through the center? So we'll do a problem where I'll show you how to do the asymptote a little more easily. This can be a little complicated, like KH and DNA, like versus. Don't worry about that. I think actually this makes it worse, this formula sheet. But it's good to have a reference just so you could visualize what's happening and all the other stuff that's going on there as well with other stuff. But let's get back to the notes now. Let's do some problems. Okay. So let's talk about number one here. Getting back to notes. Okay. So the center. You can see how the center's at 1, -3, right? Mm-hmm. And how far is it from the center to the vertex? If I count it, how far is that? 4, right? And how far over here? 4 again, exactly. And then, even though that's not a point of the curve, I'm going up to and down to. So there's actually this invisible rectangle. Like I like to call it the central rectangle, because it is in the center, obviously. But if you think about it, and let me get rid of this because it's a little distracting. So you have like a central rectangle there. And look at those diagonals. Or sorry, those asymptotes. See those asymptotes are the diagonals of the box? In fact, actually, I drew it quite well. You see how that's a diagonal, that's a diagonal. If you extend those diagonals, those are the asymptotes. How do I find those equations? Not that hard, right? How far am I rising, guys? How far am I running? But there's also another line where I go down and write as well. So I'm going to write my asymptotes like this. Y equals, actually, before I get too carried away, you guys know this, right? You might as well get used to it because you do it often in calculus. We rarely write things in slope-intercept form. Point slope's more popular. So what point do both asymptotes pass through? Nope. For this one here. For this one, 1, -3. Yeah, so you're gonna do y plus 3. And the slope is up 2, down 4. So I'll write plus or minus 1/2. X minus 1. That's it. That's how you write the equation of asymptotes. It's that simple. You know a point that both asymptotes pass through the center, which I did 1 and -3 for x1 and y1 respectively. The slope is up 2, down 4, or the down 2, right 4, which reduces 1/2, but you have plus or minus. So that's how you can write the asymptotes. So I think I've already kind of done. Yeah, I already did part B for you guys. So part B has been done already. So part B is done. For part A, so sorry I kind of went out of order, but I just did part B for you guys. For part A, they're asking to determine the course of the vertices. That's easy, just look at it. 5, -3 and -3, -3. All's good there. Cool. All right. Okay. Let's look at number 2. But in the hyperbolic equation number 1, the x term is positive, the y term is negative. Okay. So in this case, it's going to open. Oh yeah, sorry. That's what we saw in number 1. So that's what open left and right. So in this case, it switches. So it's going to open up and down. So what's my center here? Yeah, 1, -3 still. And I go 1 up. So your a, sorry. Your a square is 4 because they wrote a little differently actually. So your a is 2. Let me take it back. Your a is 2, and your b is 4. Yeah, just the way it's written. Just you have to be mindful of. I don't like the lack of consistency here. To be honest with you, I kind of think of it like this. Anyway, yeah, 2 up, 2 down. Yeah, so what's going to happen is going to look like this. So my central rectangle, that's my central rectangle, which I think I've done correctly. And it's going to open up and down. So it looks like that. And if you want to get rid of, you can get rid of that rectangle if you want. The rectangle is kind of like a foundation for the graph. It just kind of sets the tone for it. And then you draw the asymptotes and then you draw the graph afterwards. If you were to plug in, say, for example, -1 for y and 1 for x, it'd work itself out. It would make sense. The equation would be true, right? Or if you plug in, again, 1 for x, but -5 for y, again, it would work itself out. It'd be fine. So hopefully it makes sense. We're okay? Cool. Okay. Let's keep moving. For this one here, I think we're at the home stretch because I don't want to because the rest is kind of review. So once we get done with this, we'll just do homework after this. Um, divide everything by 4. You should get this. Pretty simple, right? Um, okay. Where's the center? Yeah, awesome. Good. Great. And how far am I going left and right? 1 and 1, and 2 and 2 for up and down. Good. And draw your rectangle. It's kind of a skinny rectangle, right? It's kind of like an ellipse in a way, if you think about it. I mean, if I did it more curved or circular in nature, then it's an ellipse, right? It's not that bad. Just a little extra work, right? Then I gotta draw the asymptotes. Okay, fine. Draw the asymptotes. Not a big deal. Opening left to right or up down? Left and right, because x squared is positive. Exactly. And just draw your curves and you're done. That's it. And you use the rectangle and the asymptotes as like the foundation, right, for the graph, you know? It's not that hard. A okay? Cool. And A actually happens to be 1 and B actually happens to be 2. So in this case, A is a lot smaller than B. That's different. A is reserved for the positive fraction. B is reserved. Is that your crush, Kyle? Yeah. Yeah, it's different. It's a different mindset. A is reserved for the positive fraction. B is reserved for the negative fraction. Give the equation the asymptotes. That's not hard. That's y uh, minus 2. And how far I'm going up and over? Up 2, right 1. So plus or minus 2, x plus 3, I think. Yeah. Yeah. Sorry, that's a little hard to read. The glare. Okay. Vertices, I mean, don't worry about it. I know you guys can say it's center point vertices, so. Okay. Um, go and try 4 on your own. Bless you. I'll freeze the screen again. Then we'll do 5, and we'll wrap up the notes for today. Remember, divide everything by 48 first. Well, that's kind of nasty. It was a 6. Hmm. So that's root 6, which is like 2 point something, whatever. Should we open left and right, guys? Root 6, 2 point something. Remember, c squared equals a squared plus b squared. I think oh, I didn't say the asymptotes. Let me do that as well.
Oh, no, outside.
Let me know if I made a mistake. I can make mistakes here. C squared equals A squared plus B squared. So C squared should be root 22. Sorry, C squared should be 22. C should be root 22. Let's say I'm going up root 6 over 4. I think that's my asymptote. Is that right? I think that's right. Yeah. Let me know if I made a mistake. I don't know. We're good? We agree? Cool. A little funky with the root 6 part, but sorry, go ahead. Thor, what's your question? Thor, you have a question? Oh, so there's a formula: C squared equals A squared plus B squared. That's why I'll just give you guys because I haven't done that derivation yet. What's up here? So your A squared is 16 and B squared is 6. If you add that up, you get 22. So C will be root 22, which is like 4 point something. I didn't draw it very accurately on the. I probably should have shifted this maybe a bit more. Well, I don't feel like moving. Oh, see. Well, whatever. I'm not gonna move it. So, okay. We're okay with that. It's all good. All right. Last part. Well, let me go here really fast. Classify tonic sections. So there's a fancy. Let's see what Gemini says. Okay. Okay. There's kind of like this fancy way of generalizing tonics, which I don't really like because it's too much memorization. Like if you were to have this like expanded form, like okay, ax squared, bx squared, and whatever y. Actually, that should be a y. That's a typo. That should be a y. It's on Terraform's website. But anyway, if A equals B, it's a circle, blah blah blah, whatever. There's all these like different rules and whatnot. I prefer you just kind of just think about it. So, like for example, just look at it, right? Okay, now we know if you have only one variable squared, that's gonna be a problem, right? Well, one of these has just one variable squared. Which one has one variable squared? C. See the problem. That's I know. You don't get too fancy with the classifications. Like there's a way you can memorize it, like, but it's just like if A and B, blah blah blah, like some sort of weirdness. I don't like it. Okay, now to have a hyperbola, you have to have two square terms, but they're an opposite sign, right? One's positive, one's negative. Well, which one has x1 both squared but opposite in sign? D. So that's your hyperbola. Okay, A and B are pretty close, but how do you distinguish between the two or discern? Yeah, because they have the same coefficients. Now, if I put like a 4x squared and 4y squared, who cares? Because they're the same coefficient, that's still a circle. Because at the end of the day, when you clean it all up and complete square and put in standard form, it's still gonna be a circle. So you don't have to waste your time actually doing the completing the square part. You can just kind of look at it and compare it to what we know. And then this is an ellipse, has two square terms, but the coefficients are different. And, oh, and by the way, they're both positive. Both the same sign. If I could have done negative 2x or negative y squared if I want to, sure. But the bottom line is you have two square terms, both same sign, but different coefficients, different magnitudes of coefficients, right? So yeah, so that's an ellipse. And the beauty about Desmos, by the way, if you actually were to do this in Desmos, you can punch the way it looks. You don't have to isolate y. You don't have to put in standard form. Just punch like the way it looks, and it will give you all the parameters you need. So if you want to check your work, Desmos is lovely. It's really great. So the rest is just like review problems. We'll save this for later, but at least I feel like I've got to all the shapes now with you guys, right? So we started this last week. We had 2 classes last week. We had our third class of this unit. Now we're going to start mixing things up. We're going to start looking at, moving things around. We're going to start looking at word problems, solving, doing these two at a time, solving systems of nonlinear equations. So the fun begins tomorrow, and we'll keep having fun with this over the next 2 weeks. So anyway, homework is very simple. Homework, if you guys want to get a start, you got about 9 minutes. It's 9-5, guys, just 9-5. 1 through 9. Ooh, that's a good word problem. This is like some science center in St. Louis. The roof is actually St. Louis Science Center. Yeah, there you go. That's the shape of the Science Center. I've never been to St. Louis, so I don't know. That looks kind of cool. All right. Our original school in the United States is in St. Charles, Missouri, close to St. Louis. Yeah. So that's where there were St. Rose, Philip, and Duchenne found it. Anyway, so just work through that. That's all. I'll put in Schoology. All right, and we're all set.